You know, we use them every single day, probably every single hour. But have you ever really stopped to think about what an operating system actually is? It's kind of like the invisible conductor of an orchestra, or this master translator that lets you and your computer actually have a conversation. Without it, your powerful laptop is really just a box of parts.
I mean, think about it for a second. We think in words, in ideas, in images. A computer's hardware? It only gets the language of electricity. Basically just ones and zeros. So how do you possibly bridge that huge gap?
Well, that bridge, that's the operating system. The best way to think about it is like a personal, super-fast translator. You click an icon, you type a command. You're speaking your language. The OS instantly translates that into machine language for the hardware. Then it takes the hardware's response and translates it back into something you can see on the screen. Thank goodness for that, because otherwise we'd all have to learn to speak binary.
All right, so to really understand how we got here, we've got to go back in time, way back to the early days of computing, where the first major type of OS was born from a need for just pure, raw efficiency. Let's talk about the batch operating system.
See, back then, the challenge wasn't about live interaction. Computers were these giant, incredibly expensive machines. The whole game was about feeding this beast a mountain of jobs and making sure it processed them without wasting a single, costly second of machine time. How would you even manage a queue of hundreds of different programs? The solution was actually brilliantly simple, even if it was a little impersonal. You, as the user, didn't even interact with the computer. Nope. You submitted your job, probably on a stack of punch cards, to a human operator. That operator would then group similar tasks together into a batch, like putting all the C++ programs in one pile, all the Fortran jobs in another. Then that whole batch was fed to the computer to just chew through, one job after another.
And this setup perfectly highlights its biggest strength and its biggest weakness. It was amazing for processing these massive, time-consuming tasks with maximum efficiency. But the downside? Well, once you handed over your job, that was it. It was out of your hands. No tweaks, no quick fixes, no interaction at all. You just had to wait and hope for the best.
But of course, technology never stands still, right? The focus started to shift. People didn't just want to process jobs efficiently, they wanted to interact with the computer while it was working. And this new demand gave rise to the time-sharing OS.
So here's the new puzzle. You've still got one super powerful, very expensive mainframe computer, but now you've got dozens of users who all want to use it right now. How in the world do you give everyone a fair turn without making them wait for hours and hours?
I really love the analogy on this slide. It's perfect. The OS is like a really fair parent. And the programs, or tasks, are its kids. The parent doesn't give the older kid twice as much attention. Nope, it gives both children equal time. And that is exactly what a time-sharing OS does.
It works by being incredibly fast. It gives every single process an identical, tiny slice of the CPU's time. We're talking milliseconds here. It doesn't care if one process is massive and another is tiny. Each gets its little fraction of a second to run. The OS just switches between them so rapidly that, to you, the user, it feels like you have the entire computer all to yourself. It's a pretty clever illusion.
A huge advantage here is that nothing is wasted. If a task only needs, say, 2 milliseconds of its 10 millisecond time slot, those extra 8 aren't lost. They get handed right over to the other tasks. The main drawback, though, is that all this constant, rapid switching can sometimes get messy. Imagine two programs trying to update the exact same file at the same time. If that timing is just a little bit off, your data can get scrambled. That's the kind of communication problem that can pop up.
So we've seen the evolution from one computer handling many jobs to one computer handling many users. So what's the next logical step in the story? Well, of course, it's handling many computers at once.
As computers got more common, the new goal was getting them to work together. How could we possibly connect separate machines to share things like files, printers, or maybe even their processing power? This is exactly where networked systems come into play. And there are really two main flavors of this. On one hand, you have a network OS. This is your classic client-server model. There's one main server that's the boss. It manages files, security, access, and all the other client computers connect to it. Then there's the distributed OS, which is a totally different philosophy. Here, all the computers are interconnected, and they work together like they're one giant computer, sharing the workload between them. Okay, so let's look at the crucial trade-offs. With a network OS, you get fantastic centralized security, but it has a single point of failure. If that means server crashes, the whole network goes down. Poof. With a distributed OS, the huge benefit is that workload sharing, but its weakness is the links between the computers. If the network connection itself breaks, the system fractures into a bunch of isolated pieces.
Now for our final major category. And for this one, the stakes are incredibly high, and every single fraction of a second counts. This is the world of the real-time operating system.
The problem here isn't just about being efficient or sharing resources. It's about life or death timing. In some systems, a tiny delay isn't just an inconvenience. It's a catastrophic failure. So how do you build an OS that can guarantee a response within a fixed, unbelievably short deadline?
And we are talking about some incredibly critical applications. Think about missile defense systems that have to track targets in an instant, or scientific missions at NASA where precise timing is absolutely everything. Even hospital equipment that's monitoring a patient's vital signs. These are systems where lag is just not an option.
Just look at that number, less than 1 millisecond. A real-time OS is designed for one primary goal, to give a correct and lightning-fast response every single time within a guaranteed window. This level of precision and reliability is incredibly powerful, and as you can probably guess, it's also incredibly specialized and very expensive to build.
So, from batch processing to real-time reactions, we've seen how operating systems are really just specialized tools for different kinds of jobs. Now, let's just quickly touch on two key features that modern operating systems use to give us the powerful experiences we're used to today.
First up, multiprocessing. This is pretty straightforward to picture. Instead of just one CPU, one brain in your computer, a multiprocessing system has 2 or 4 or sometimes even more. It's all about adding more raw horsepower to get more work done faster. Simple as that.
And then we have multitasking, which is something we all experience every single day. The best way to think of it is as your OS's amazing juggling act. When you're browsing the web, listening to music, and writing an email all at once, that's your OS just flawlessly managing multiple tasks. It's really the modern version of that time-sharing idea we saw earlier, just happening at lightning speed right there on your own computer.
You know, from managing batches of punch cards to coordinating global networks and making these split-second life-or-death decisions, operating systems have always evolved to meet the next big challenge. Which really leaves us with one final thought. What comes next? What new incredible problems will the OS of the future need to solve?